We had a pretty full room this morning. Okay, so listen, I'm Pepper Hastings with Innovative IDM, and welcome to VFDs for Your Modern Facility. It's a 40-minute webinar. We will be done in 40 minutes or less. That's my promise to you, and we will not hold you hostage. Our presenter today is Edward Tom, and Edward is a applications engineer with Yaskawa Drives. He's been with Yaskawa for 16 years. And he knows his stuff when it comes to VFDs. It's a great guy to have in the room this morning. Let me admit a few more people. Jim, Jake, and Brian coming in. Edward is a graduate of University of Illinois, Urbana-Champaign. So he's right at home up there in Illinois and working from home today, right, Edward?
You got it. You got it.
So I'll tell you what, I'm going to turn it over to you. You've got you got a few minutes to let these people know about what you know about VFDs in your modern facility. So go ahead.
You got it, man. Well, thank you everyone for joining. Really appreciate you guys taking the time out this morning, spending the 40 minutes with us. And Pepper and Innovative IDM, thank you for the invite for being able to do this. I actually really appreciate being able to do this and share what I know and hopefully be able to give you guys some new nugget of information, if not a good amount of information that you guys can take and work off of. As Pepper mentioned, I am Edward Tom. I go by Ed. One slight correction that I didn't mention to Pepper is that I am a product manager over at Yaskawa. So I handle all of our microdrive product lines, but I'm very familiar with a lot of our products, so including the stuff that you see up here. I do want to give a few minutes to talk about our to kind of just go do an overview of Yaskawa real quick in terms of who Yaskawa is. I think there are some that you may be familiar with the name, and others may be kind of looking at it going, well, who are these guys? And at Yaskawa, we are a motion control company. We make drives, we make servos, so that's the motion side, and robotics. And that's what we focus on. And we've been doing that for many, many years. In fact, by the numbers, if you take a look, we've been around since 1915. And we have done a good amount of units, not just in the past year, and not just in 2020 in terms of the number of units that we've sold, but just in the lifetime of Yaskawa. Here, as you can see, some of our employees are pictured here. If you guys ever get the chance, and when things do clear up a little bit, I will recommend coming up and checking out our facility and kind of seeing what makes Yaskawa capable of doing the things that you see up here. When it comes to our sales and our manufacturing excellence on there, see what a world-class facility that we have and be able to take that back with you. Now, we do have a corporate vision. One is we want to empower the innovation, not just innovating drives and the technology that's out there, but also taking our products and be able to help you innovate and produce the products that you guys are going to be involved in. And with that, help you elevate your business, take that to the next level. And in the end, take it and be able to have something that can enhance your life, whether it be giving you more time, giving your factory more time, or for just the people that you're serving with your products, be able to give that enhancement, be able to enhance their lives in many different ways on there. And how that now leads into, and I'll take that and lead it into just the various different applications that are out there. When it comes to electric motors, hopefully, if you guys are in some type of manufacturing plant, you're going to probably find some type of electric motor running your application. And if you guys have a moment, I really would appreciate if you guys want to be able to just kind of send a chat message and let me know what type of application or industry that you're in. I am actually very curious on that. But some of the stuff that you'll find electric motors on are compressors, extruders, and then jumping into industry portions. You may find it in oil and gas, in pumping, all sorts of different industries, something you'll find an electric motor on. And what's important about the electric motor in general and in that application as it ties in is that an electric motor worldwide, globally, uses 45% of the world's energy. And how that's important is that that actually constitutes a large portion. We thought that, you know, turning on your lights and all that was important, but to be able to supply all the energy, supply the water, be able to, in this case, have a pump jack, be able to pump out oil or any type of fuel from the ground, um, all of that is contributing to that global usage on there. And what we want to be able to do is take that and be able to help sustain the amount of energy usage that is there. And by doing that, by having a drive be able to run some of the applications, you're now going to be able to help reduce the energy usage on there. So I'll get into that a little bit more in terms of a comparison, but this is something to keep in mind is how much energy a motor really does use as we're looking at some of these applications. The pump jack I mentioned, we certainly have a dynamometer. This one, there's a dyno for if you've got a test stand. Some people, I see people have put some messages in here. Printing machines are also great ones when it comes to being able to use a VFD that's in there when it comes to running the rollers that are on there and the wind up and unwind portions of that. Now, some of you guys may be already using motors on a VFD, and some of you may still be running, if you are running an electric motor in your facility, you may be using that motor and running it across the line. And with an across the line start, what you have is a motor that's going to be running at a constant speed. The motor itself will be a constant speed depending on the line voltage and more importantly, the frequency that of the line that you have coming in there. Now, some of the things about running a motor across the line is that when a motor's running at full speed or running across the line, it's always drawing current. It needs current to be able to magnetize, be able to start spinning that rotor on there. But when you have that current running through there, you're going to get system losses. So if you've got current running through the line and through your wires, there is some resistance in there, and that is going to result in some of the losses just to get from point A, from the power company all the way over to your machine. You're going to experience some of the losses, and something to be taken into account. The other is low power factor. And I'll get into a little bit more about power factor later on, but ultimately power factor can be looked at as how efficiently are we using the power that's being supplied to us. And a motor, again, this just goes back to a motor running across the line. It is going to result in a lower power factor depending on the load that's being put on there. The other thing is that if you are regulating using a motor that's running across the line, or even during just starting and stopping a machine for various different reasons, say you need to stop a machine because there was there might have been a small jam, you need to stop it and then restart it again. Well, every time you start a motor up across the line, and this is assuming not using any type of a soft starter, you're going to see somewhere in the order of 6 to 8 times that motor nameplate current show up. And when you take a look at that current or with that presence of that current that's on there, what's going to happen is that you're going to have electrical stress of the system, of the drives that you are, not the drives, the wiring that's out there, the motor that's there, and anything that's in between there that is connected. It is going to get stressed. Mechanically, you're also going to see the machine itself potentially get some mechanical stress. So you're going to have a motor that is at a complete standstill. And imagine taking that motor and taking it up to full speed in the shortest time possible. I mean, depending on how much load you have on there or the inertia that's connected to that motor, we're trying to get that unit to go from 0 to full speed. I'll assume an 1800 RPM motor. You're trying to get that to 1800 RPM in less than a second, or if there's a lot of inertia, maybe just over a second. That's a lot of torque on there. And imagine continuously doing that, stopping and starting, the amount of torque and the amount of just impact load and twisting that you get in there. So that's the type of mechanical stress that you're going to see in there. And eventually you're going to have to work through that. I mean, that's something where with enough of that, you are going to see damage to the mechanics of it, and possibly replacement. So that's where your maintenance and preventive maintenance will come into play. Now, last bullet point I have on here is that depending on when this happens, and depending on the power company, you may get a demand charge that occurs on there. So you may have a 10 horsepower motor that you start and stop, no problem. But imagine if you start getting into larger and larger motors. So say you've got a 300 horsepower, 500 horsepower. And during the peak times, what you could potentially run into is if you just hit it just right, start it up at that right time, or maybe multiple motors start up at the right, just at that time, what you're going to see, you're going to get a surge of current, and the power company is going to look at it and go, well, you've got enough, you've asked enough demand, we're going to charge you for going over a certain amount. So that's certain things to really watch out for at times when it comes to cycling that motor on and off and using it as a means to control it. Now, you may be looking at, you may have taken the next step and said, well, it's great, we don't cycle the motor on and off. We actually do regulate our systems. We do have some type of speed regulation on there. And some of the mechanical methods that some people may use, if you're regulating air, you may have a damper. If you're pumping, you may have a valve, and some may even use a variable pulley. Back in my days, when I was at a distributor, I used to go out and actually have to go and either repair or install Reeves drives. They were these variable pulleys, electrically controlled most of the time, pulleys that gave you that variable speed capability. But when you have something that is mechanically controlled in that sense, you ultimately have something that is capable of wear. And that is still an additional component for you to still be a little bit worried about down the road. Not immediately, but always down the road. When it came to those Reeves drives that I mentioned, one of the things that we would find, or that I would see, is that you would have those pulleys start wearing away with time. Over time, the V grooves on there would start getting, the belts would dig into the V grooves more and more and more onto the pulleys, and to a point where you didn't get much adjustment. Sometimes it was to a point where you would get a sudden jump in speed because it would go from a groove to suddenly to a new spot onto the pulley, and then you get this new speed, which, well, you didn't really want. You were trying to get a slightly better regulation on there at that point. So now you're looking at a mechanical replacement there. I've already mentioned one of the issues of running a motor at full speed. You've got your constant loss on there, and depending on the loading, and depending on depending on how heavily loaded it is, you're also looking at the amount of the power factor coming into play with it, or how efficiently you're using that power. Now, you may also run into a case where you would have to cycle the motor on and off just to be able to regulate the control. Now, I'll go back to the Reeves drives, is that there was only so much speed control that we had on there. So you can only go so low when it came to the speed. So there are points where if you run to a certain point, you may find out that I can't get any slower. I'm actually putting out too much at this point, so I need to stop the machine at this point, at this moment. So that's what you may end up doing at that moment, is just shutting off the machine and then restarting it, and then seeing that current coming up. So those are some of the things that you may run into. So why use a VFD? Well, going back to that regulation I mentioned earlier, a VFD has a wide range when it comes to being able to regulate the speed of it, or the system that you have out there. So whether you're regulating around pressure, or around the amount of output, or maybe it's the amount your conveyor needs to push to the next section, or is transporting material to the next section, you have a finer control of that when using a VFD. Now, I will take a step back here real quick. I threw out VFD. I think I threw out drive out there. What exactly is a VFD? What is this? Well, in this case, a beige box, but black box that's out there that is controlling my speed. And a VFD is ultimately a variable frequency drive. It's been known by other terms, and I've used it interchangeably as a drive or adjustable frequency drive, adjustable speed drive, and the slight misnomer, but it's also been called an inverter. And I'll get into the topology of the VFD and why some people refer to it as that. But that's some of the names that you'll hear for a VFD or a drive. Now, I'm going to be talking about all this different magic that it's going to do. At least for some, they may find, hey, this is great. It does all these things, but how does it actually work? What does a VFD actually do to make all of this happen? And right now, what we're doing is your power company is supplying you a fixed voltage and a fixed frequency. And there's not much we can really do about that when it comes to taking that voltage and trying to control the speed of your motor at that point. We talked about the mechanical methods, but that certainly has its drawbacks to it. But what we found is that in order for you to control an AC motor, vary the speed of that motor, if you adjust the voltage and the frequency to it, you can actually change that speed of the motor, going from a faster speed to half of it or even lower, and hence giving you that control of the motor itself. Well, I can't really just take the line voltage and manipulate it right on the spot, at least not easily. So when VFD technology was first created, what they did was they took the incoming voltage, that fixed frequency, that fixed voltage, and we take it and we convert it to DC. And from DC, we take that and then pulse it out, regulated pulses, and send that to the motor so that it gets that equivalent voltage and frequency that we want. And the magic behind it, or really the hardware that goes behind it, has to do with the diode bridge. And a diode bridge in there is really just like a valve, like a check valve. If the voltage on the front side, your incoming side, is higher, it'll send current over to the DC bus, charges that up. And if it's lower, nothing happens. So it only occurs, so there's only flow through there when there's actually higher voltage on the input side. So now that we've got the DC bus charged up, we now need to take it and turn it into that regulated pulse voltage, the pulses that we were talking about. So now we're taking the DC, and with the IGBTs, the insulated gate bipolar transistors, we're pulsing that and sending it out to the motor, and then regulating it so that it gives us that voltage and frequency that we were looking for, that I was mentioning. And now we've got that control. So the basic topology is there, but how does it really help me? What is it doing? That's great that it's taken this input voltage, it's converting it to DC, it's pulsing it out. Well, how does it really help me? Well, one, we're going to have the improved power factor. So it's able to use your energy that's coming in more efficiently. And I will get into that soon. And your system losses are also going to be decreased. And it ultimately will be taking your power in that you're using and be equal to the amount of power that you're putting out on that motor. So I did mention I'm going to talk about power factor and how efficiently it draws it. So power factor is the combination of how efficient or the overlay or displacement of your voltage and current. And one way I look at it is, think about trying to move a box. You have your friend, who I'll call voltage, who is pushing the box. And I'll call you current. You're the one pulling the box. Now, if your buddy is pushing the box at one point and you're not really pulling at that moment, that person's doing all the work. Well, as they might have tapered down, so if I follow the waveform on here, as they begin to taper down, you might find that you're going to start pulling. And you start pulling the box, everything's going great, and they come to a complete standstill, and now you're doing all the work. Well, that's what the power factor is. It's that offset. You're not quite synchronized together, so you're not putting that effort in there in such a good, efficient manner to really move this box. So what we want to do is get those two synchronized so that when he's pushing, you're pulling at the same time, and it gets you that efficient movement of the box. And that's what we do want to accomplish with this. So what does that mean? That means that we're taking the reactive power, the energy that's just circulating inside, and we're going to try to reduce, and we're going to reduce it with the drive. Now, why is this reactive power that I'm mentioning a problem? Well, the reactive power makes up the kVA, and that's what power companies charge you for, kVA. How much am I sending out at that moment? So the more kVA that it needs to do, the more you're getting charged. It also means that the higher kVA that it needs to supply you, the larger transformer that they need to put out there. And also more, and I've already mentioned the higher demand. So think of it like getting beer. When you get a certain glass, if on your end, if you get a mug of beer, you want more real power in that. You don't want too much of the reactive power. You want that real power. You want that liquid. You want the good stuff out of there. So you want to be able to take it and minimize that. And that's what the drive is going to help you do on the power side, is minimize the amount of reactive power on there and get you more real power, or in a sense, you'll have more real power present in there versus a mix of the reactive power. So your power company is going to be happy because now they're going to say, hey, my kVA that I supply you is going to be close to your real power. You're going to be happy because you're not going to get charged as much because you're not requiring as much from the power company at that moment. So that's a power factor improvement on there. And as we take the reactive power on the line and drive it closer to zero, as I mentioned earlier, your parent power, the power that your power company, the power that your power company needs to supply is now closer matched to what you need. So no extras that they're going to charge you for. So when you charge you for that mug of glass, they're not going to charge you for that extra. Now you're not getting that all that foam on top of it. You're getting more beer coming out of it so that you can get a good drink into your system. Now, I wanted to look at something a little bit differently too. So that's power factor. But now I also want to look at the current, because the current that we talked about earlier is also going to affect the amount of losses that you have in your system, how much you're drawing from there. Now, I'm going to assume that you're running a motor across the line. So you've got an across the line starter, and we're going to compare it to a drive. And I'm going to use a 100 horsepower motor as my example. So using this particular motor, if I was drawing its full power at 100 horse, I'm going to be seeing about 113 amps on there. So not too bad, reasonable. But on a VFD, I'm at 107. Same motor, but we've put a VFD in front of it. Slightly less losses on there. Okay, well, maybe it's just a little bit of calculation error, we might say. Now I'm going to drop that to 50 horsepower, 66 amps. Now, if I follow the same pattern, you might go, it's going to be lower. Well, definitely. We're now less than half the line current required on there. So now the amount of current that's out there, the amount of losses in your system have also decreased. Now, what if I'm just running my motor across the line? I have no load out there. It's just running. I'm waiting for product to show up in there. Well, there's going to be your reactive power that's out there. The energies, the current and voltage that's needed, ultimately the power that's going to be needed to get that motor spinning. I'm going to still need to draw 40 amps regardless at this point. Well, what about with a VFD? I'm not running, the motor's not running, or let me rephrase, the motor's running, but there's no torque being produced on there. It's just spinning at this point. Well, the amount of current that you're going to see coming out on the input side, or the amount of current you're going to need, is going to be pretty close to zero. It's going to be, in this case, about 1 amp. So big difference when it comes to the different amount of loading that you're putting on there. So at a quick question, is the line current change appearing in reactive power instead of real power? And the answer is yes. When it comes to the current changes, you're always going to have the magnetizing current inside the motor. That's always going to be present inside in the motor, and on the line side, that's always going to be present. You're always going to see that on the line. On the VFD side, the reason why that line current is lower, and we're also going to be able to get, we're going to see lower line current, is because that magnetizing current is still there on the motor side, but the drive is a little bit on the, will shield that a little bit, because now it's just circulating inside the drive. We don't need anything on the input side, so it just keeps recirculating in the drive. So now we only draw power when we need to. And that's the beauty of the drive, is that it only draws power when it truly needs to power that motor. Now, I'm a mechanical. You know, I just went through an electrical example. Being the mechanical that I am, I want to look at it going, okay, well, how does this relate to my mechanics of things? Well, I had my power equation for electrical. Mechanical power is speed times torque. So how does that really work out? I've got my speed, I've got my torque, and the product of those two gives me my power. So if I am at zero speed, then I have zero power. If I have zero torque, I have zero power. Well, what if I am at zero speed and I'm putting as much torque as I possibly can? So think about that boat that just seems to be rusted and you're trying to apply up as much torque as you can. To you, you're thinking, hey, I'm putting a lot of power in. But according to the equation, you're actually putting work in, but you're not putting any power in, put it that way. Well, how does that equate back to electrical, the VFD portion of it? Well, that is still proportional. So if I've got a motor that's not drawing current, or it's drawing very little current, then I'm going to be pulling very little power. Same with the voltage. Because we're regulating that voltage, if our voltage out to the motor is very low, then that times whatever current is going to result in low power. In fact, if you recall back earlier, I had shown where if you're doing an across the line start, you had current that was spiking up. So from an across the line, you might have seen something where it jumps up, comes back down, and then stabilizes. So poor drawing from a mouse, but to get the point is that you now have a high current spike. Well, if I take the same mechanical equation into effect, I was at zero speed. So if at zero speed and I'm just barely ramping up, guess what? My power, even though I'm putting out 150%, 200% torque to get the unit running, my power in the end is going to be low, even just to start that motor. I'm not going to see that high current spike that we talked about for across the line. We are going to see a low amount of power being pulled through there as we get the unit up and running and ramped up to whatever speed that you're looking for. Now, that's looking at from a power standpoint, what we gain off of there. Some additional things I mentioned: you have less mechanical wears when you jump over to using a VFD. Your system complexity certainly goes down. The reason for it is that instead of having all the gearboxes, pulleys, and all that, you may now just have a drive, a motor, and that's directly connected to your load. Now, you may find out you may need a gearbox for various different reasons, but it's something where it will depend on the system that you have. And the regulation is going to be a lot tighter when it comes to it. You have a wider range of regulation, but also a tighter regulation because we have a fine control of that motor. So that's the basics of how a motor operates, the basics of a VFD, and also the benefits that you would get off of using a VFD. Now it's, how do I pick a VFD? What do I need to do? If I'm looking at an application and I call my innovative IDM rep, I say, hey, you know what? I'm looking at doing this. What do I need to tell them? Well, one of the first things I would recommend is the application. Let them know what application that you've got. Their years of experience over there will help you will help guide you and also be able to help be able to supply, be able to get you to the right drive at that moment. The other is the incoming voltage. What's important with the incoming voltage is that that voltage will dictate what voltage drive you get. There is a distinct 200 volt class or 240 volt drives. There are 480 volt drives, and there are also 600 volt drives. So we do want to know that incoming voltage that it's going to be that's going to be wired to, so that we get you the correct drive the first time around. And certainly the motor horsepower or the current. If you've got either of those, that helps a great deal because it is going to be different sizes. So imagine a 1 horsepower drive, you can get a smaller drive compared to a 100 horse, 250 or even larger. It is going to be a different drive. So we are going to want to get something that is tailored for that. Now, also think of it from a contactor standpoint. If you've got a small motor, you can use a small contactor. A big motor requires a bigger contactor. So a very similar concept when it comes to knowing your voltage, knowing your current. And again, that application is important so that the innovative guys can definitely help you guys out when it comes to tuning that and be able to help out. Some additional things to consider. One is motor control, the type of motor that you have out there. Now, right now, the most popular is the induction motor. And that particular motor is going to be something that you'll probably find all over your plant. But you might want to pick a drive that's got the capability of either doing a permanent magnet or a synchronous reluctance. And the reason for it is that those two motor technologies are starting to emerge more and more. And you may find that you might find that there could be a shift on wanting to use those versus the induction motor for the energy efficiency. Another one is you might want to find something with a good auto tune so that it can get a very good control of your get good motor model and have very tight control of your application. So I mentioned that regulation earlier. This gives you the ability to even regulate more finely than that. And what's important is find something that is reliable, that gives you near tripless operation. Your application that you have, the machine that it's running, it's important to you, it's important to your company, and you want that thing to run for as long as possible, and you want to avoid that downtime. And so try to find something that gives you that. And the innovative guys will definitely be able to help you out. My recommendation certainly is going to be our Yaskawa drives. Now, this has been picking up more and more steam when it comes to networking, having the ability to connect up to whatever network system that you have out there. And it is going to be a variety. So you may have DeviceNet or Ethernet IP, but you want something that gives you that flexibility to connect up. Safety is becoming a bigger concern. Have a drive that is able to get you that safety rating for the machine for as little parts as possible. So using as few components as you can to get you that machine safety, get you that machine rating that you're looking for, but also be able to get you up and running in case you do need to activate the safety functions on there. The longevity, with the Yaskawa drives, we test our drives rigorously, and and the drives are designed to operate for 10 years of maintenance free, of kind of one of those set it and forget it moments. If you're an OEM sending machines, we're designed for all the different worldwide regulations, from locally UL, CE, to in Australia, CTIC. And the conformal coating on the boards are going to give you that extra level of protection for the application so that you don't have to worry as much about the drives. So what we want to do at Yaskawa, what we want is to make that complicated simple, make it a lot easier for you guys to be able to not only pick out the drives, but also be able to be not as worried about the machines. One thing I had forgotten to mention early on is that in the chat window, before you guys had gotten in, I had put in 3 different links in there. First link I have in there is for the energy savings predictor. If you want to be able to try to calculate how much energy savings compared to running across the line, it's a great tool for that. The product selector, I mentioned earlier when it came to the information that you want to know about picking out the drive, the product selector is out there to help you choose and compare the different drives that we offer. And if you want to get a feel of what our drives are when it comes to programming, there's also the programming simulator. And that'll give you an idea of what it takes to be able to navigate through our drives and what it feels like. You know, how different is that? Or maybe before you even get out into the factory floor, you'll get a good feel of how to program up a drive. So I think I pushed almost every minute of it, but hopefully you guys enjoyed it. I definitely enjoyed being able to present the information. Any questions that you guys have, and I'll toss it over to Pepper at this moment.
Yeah,
With
that's
that.
great. Ed, thank you. That was 37 minutes. I appreciate it. Thank you for respecting our audience's time. I had a couple of people send a direct message to me that were some questions. You might have had one sent to you too, but one person asked, what type of maintenance is needed for a VFD?
All right. So for those that are new to VFDs, I'm going to compare it to a contactor. So a contactor, you probably need to maintain it in terms of the spring. There's mechanical springs, the contacts replacement, all of that. Well, the drive doesn't have all of that. The maintenance, when I say that you're looking for really, is just the cooling fan and the capacitors. And the cooling fan is probably going to be your mechanical component that's in there, is the one that you'll worry about most at this point. But that's also designed for that 10 years of maintenance free, so that every so often you can go take a look, make sure everything is clean, unclogged on there. But typically after about 10 years or more, that's about when you might be looking at replacing it. And really that's about all the maintenance you may be looking at for it.
Okay, and this is kind of like a college class. If anybody needs to bail out, go ahead and roll. But if you want to stick around and ask questions, feel free. I had another one that said that, are you still able to select a VFD if you're not sure of what your application is?
Oh, definitely. So even if you don't know the applications, we do have, all the drives are designed as general purpose. The biggest two, really, I should have said, the biggest and most important piece of information is the input voltage, or the voltage that you're going to be feeding on, and the horsepower or current. Those two are really the most critical pieces. The application helps us tune it in, and also helps the innovative guys and our guys are, as well, be able to help you, guide you through some of the features of why certain things are selected.
Yeah, Ed, take a look at the chat box there from Daniel to everyone.
Yeah.
You see that?
You discuss how to identify if an output filter is needed, Dvdt, sine wave. So when it comes to using any type of output filtering, one of the more basic stuff that most people would look at is going to be the amount of distance between your drive and your motor. And that mostly is measured by how long that cable is going to be. Typically, the farther out you go, they'll recommend between an output reactor to Dvdt filter. And then if it's a very long distance, there's going to be a recommendation for a sine wave filter. And those are mostly recommendations. When it comes to actual usage of it, myself, I usually recommend taking measurements at the motor conduit box to see what that voltage, what that PWM waveform looks like. Because what those filters that you're asking about, Dvdt, sine wave filters, what they're helping to do is trying to minimize the amount of reflective wave and keep that peak voltage down. And the best way really is to take a look, see the severity of it, and then from there be able to then determine the best choice of filter. Because as we move up from reactor to Dvdt to sine wave, you certainly have a cost difference as you go up there.
Okay, and then G said, oh, I'm sorry, there was one before that. I can address the one from G Selva. It said, are we able to get a copy of the slide deck and a link for the energy comparison? The slide deck is kind of your call, Ed, since you own it, but I will definitely be sending out an email to everybody. This webinar will be available on demand. You can forward it to any of your colleagues in the plant that might feel like they can get something out of it. And I can also put all the links to the energy comparison and all that in there as well. Slide deck's up to you, Ed.
No, I will. I'll pass that along to you, Pepper. So
Okay.
for those that want it, they can certainly have that.
Okay, there's another one that just came in. Can you see that one, Ed?
Yeah, having to do with the supply chain. So that one is a difficult one. Certainly, I don't think anyone is shielded from the supply chain issues to this day. So we definitely will be seeing certain things happen. Our stocking is usually on the higher end, so that we do try to keep as much material as we possibly can to be able to get through this. But from what I'm seeing with the severity of the supply chain issues, I personally don't think that we are going to come out of it unscathed. We probably will get touched by it a little bit, but we certainly have mitigation techniques to try to make it so that we get products out to all of our customers. And we are working hard on that.
Right, and Yaskawa drives are assembled in the United States in locally, basically, so that's a plus. You can just get the raw materials, correct?
That is correct. That is correct. Yeah. So being able to have all of that is something that helps a great deal. I did see one show up here.
Yeah, there's another one right there.
How constant is low speed torque and low of Hertz practical? How much influence does carrier frequency impact motor heating? That's a good combination of questions in there.
What was the question again? Because I think he sent it directly to you.
Oh, okay. How constant is low speed torque and how low of Hertz is practical? And how much influence does carrier frequency impact motor heating? I'm going to hit the second one first. The carrier frequency certainly will have an impact on the motor heating. What we're finding is that the carrier frequency, depending on the motor design, could have very minimal effect on there. So between using something that's say 2 kilohertz to 15 kilohertz, what we find is that there could be a couple degrees difference. So again, motor dependent, it is highly dependent on, can it tolerate just a few degrees C difference on there. In terms of the constant, how constant is low speed torque and low end of Hertz, it depends on how we define low speed or how low of a speed we're talking about. But when it comes to the low end speed of that, we can get down to practically near zero. Depends on the configuration. If we're using an encoder, we can pretty much be right at zero speed, hold torque. And the practicality of it is dependent on a lot of the different applications out there. I will say that for a pump, you might go, I will say that low speed and low torque or high torque at that portion is going to be not really important, because they're more of a variable torque application, just the application type. But an extruder, you may want to be able to run the low speed. You may be able to run it at, say, 50 RPM output of the motor and still be able to produce 100% or 80% torque. So it really varies when it comes to the answer. It depends highly on the application, but the practicality is always dependent on how you want to design that machine and where you want to and how you want to run it. So hopefully that answered some of the questions that you had on there. I think that came from Jeff out there.
Yeah, we have another one there. It's kind of a 3-part question.
Let's see. So this is from G Selva. With the difficult power source at remote sites, does AC/DC filter help the VFD performance and longevity? This AC/DC filter. When you're saying difficult power, I'm going to assume that the power is not very stable. You might have voltage fluctuations and maybe even frequency fluctuations. And if that's the case, having a drive certainly will help. But a drive is only as good as the amount of fluctuations on the front end. There is a certain amount that it'll tolerate. But in the end, we'll be able, because of the topology of it, because of having that DC bus in there, we'll be able to filter out a decent amount of it. Now, if your voltage fluctuates, say from 480 down to 400 on a very regular basis and very repeatedly, in short time frames, then I think there's going to be definitely a lot of other issues besides just the VFD that a VFD may run into. And let's see, looking at the example, they've proposed a Yaskawa U1000 to solve the harmonic distortion to deal with a difficult power source. So the U1000 is a good solution for from a harmonic standpoint. When it comes to the power source, the U1000 will certainly help, and it also depend on the voltage, or really depend on where you're operating on. So I mentioned earlier, when it came to the motor, we will run at various different voltage points, depending on the speed that you need. And if you're running at, say, half speed or 3/4 speed, the U1000 or even just the drive in general will be able to help regulate that very well. So you're not susceptible to that distortion on there. It's as you're getting closer and closer to full voltage and full speed. That's where I think even a across the line motor would have some challenges on there.
Ed, thank you so much for your time today. We appreciate you stopping by to be with us all. We had probably 60 people in the room, so it's a popular subject, VFDs, and we're happy you took the time. We look forward to having you back again sometime, Ed.
Oh, it'd be my pleasure. Definitely be my pleasure. So thank you everyone for attending. I think there's a few more, but we can definitely address those offline with you, Pepper.
Oh, sure. I mean, if you had some questions, great. I mean, if you had some to you.
Yeah,
directly,
there's a few that came in privately over here.
Go ahead and tackle them. They can stick around to hear it.
Okay.
Yeah, everybody else might like it too.
Yeah, I really, it's more of a time. So I really appreciate anyone staying there, and I get that I'm holding them longer. So I've got one that says, how much maximum cable length in output side is there sea level affect the VFD? Does the sea level affect the VFD life? So maximum cable length on the output side, there is not anything that I've seen that's been unusual for it. It's hard for me to answer because some will recommend a maximum cable length of, say, 100 meters, but we've seen our G7 drives, U1000, I think it's also seen long cable lengths of somewhere between a 1/4 mile to more than that. So it's hard for me to say, hey, is there a absolute maximum? The answer is we definitely need to worry about voltage drops and reflective wave, but if you're able to get it out there and we're able to get the voltage to the motor, and depending on the design of the motor, you can run a very long distance between drive and motor at that point. And then the second part here was the sea level. I assume you're talking about the altitude. The altitude, actually, we have different, many drives have different D rates for the altitude that you're going to be applying the drive to. So as you go higher and higher, there is a D rate for the drives because of the thinner air and reduced cooling that's up there. But if you adhere to the D rate charts, typically not a problem when it comes to the life of it. You'll still experience the same lifetime as if you had sized the drive for we'll say 1,000 meters and below. Permanent magnet and synchronous, let's see here. Are permanent magnet and synchronous reluctance motors less affected by varying the carrier frequency compared to an induction motors? I apologize, G Selva. I actually don't have an answer for that one. I'm not well versed enough with some of the newer motors to be able to answer that. So I do apologize for not being able to give you an answer right now, but that is something that I'll take a look into and send something to Pepper. A couple more here. Let's see. Can we use the output side contactor normally closed? Can we use an output side contactor? So applying an output side contactor, I would put some caution in there in that you do want the contactor closed before the motor, before the drive begins to output. Some people sometimes try to use a contactor to open and close and use that as a means to control the voltage to the motor. And that's not recommended at all. Think back to the example I had of across the line starting. That's what you'd be doing if you had an output contactor that you're opening and closing while the VFD is outputting at that point. So you do want to make sure that if the drive is running, output contactor stays closed. If it's not running, no problem. You can open that up. But try to be, I would say, I would offer caution when it comes to opening and closing that up as the drive is running at that moment. So, and I think that is all of them. So for those that stuck around, thank you very much. I realized I went at least 12, maybe even 15 minutes over. So thank you much for those that stuck around.
All right. Well, thank you again, Ed, and thank you everybody for showing up. I'm going to end the meeting now and look forward to seeing you at an upcoming webinar.
Thank you, guys.